Today's topic is on half-life, and we're going to be looking at half-life graphs as well as how to calculate certain problems. Our learning targets include being able to use a graph to answer questions about half-life and to perform calculations for half-life problems by solving for a missing variable, which could include the final amount or mass of a radioisotope or the initial amount or mass of a radioisotope, the number of half-lives, the total time elapsed, and the amount of time in a half-life. Let's take a look at this graph depicting half-life. So you'll notice that on the y-axis, we have the amount of radioactive items in percent form. So oftentimes you'll see the amount represented as a percent, but understand that sometimes you might see it represented as a decimal. So 100% divided by 100 is simply 1. So you might just see a 1 at the top representing the whole or the entire sample. You may also see the amount represented as a fraction or as a ratio. So you might also see 1/1, but understand that at time 0 at the very beginning, the sample that will be shown is 100% of the sample given. It represents the whole mass or the whole quantity of the isotope that you're dealing with. So again, sometimes it'll be shown as a percent, sometimes it'll be shown as a fraction, as a ratio, or there may even be an instance where you have, instead of a percentage or a fraction, you may have a mass. So this might say 100 grams or 450 milligrams. Just understand that whatever amount it is that you see at the beginning, the first bar or the first point at time 0, that represents the entire sample. So the half-life is our way to express the time required for the number of radioactive nuclides or radionuclides to decay to half their original value. So you'll notice that after the first half-life, which is the second bar, so for this particular sample, you can see that the half-life is 5 years. It takes 5 years for half of the sample to decay, so only 50% of it is then radioactive, and that represents the amount of time in one half-life. So this is one half-life. After another 5 years passes, okay, so 5 plus 5, that's 10 years now, we are down to 25% of a radioactive sample. And then if you add another 5 years, 15 years have passed, half of 25 then is 12.5. So 12.5% of the sample is still radioactive. So what's happening is that the original isotope, the original radioactive nuclide, the parent isotope, is decaying to a more stable daughter isotope with every passing half-life. Now, one common misconception is that people think that the isotope disappears after every half-life. Part of it disappears. And that is a misconception. That is not true. What's actually happening is that the amount of the radioactive sample is decreasing by half. So this yellow-orange section, notice the key, represents radioactivity. So if, say we have a 100-gram sample, then this entire first bar, 100 grams of that sample is radioactive. That's what we're starting with. But after one half-life is passed, we still have 100 grams. This bar still represents 100 grams. However, only 50 grams is still radioactive. The other 50 grams, let me write that over here on the corner. The other 50 grams is stable, is a more stable isotope. Okay, so after 10 years, only 25 grams, if we were saying that this initial sample was 100 grams, this is 2 half-lives. Only 25 grams will remain radioactive, and then that means for this sample right here, 75 grams has now become stable. Okay, so we still have 100 grams. Every single one of these bars represents, if we were saying that the first bar represents 100 grams, then every single one of these bars is still 100 grams. It's just less and less of it over time is radioactive. Okay, notice the key down below. It shows you the black and white circles or molecules that are represented there are non-radioactive, so they've become stable. Another thing to note is that the half-life symbol is often expressed as T with a half as in the subscript. So it's important to understand that different nuclei undergo decay at different rates. Each isotope has its own characteristic half-life. So let's take a look at some data here. So we have isotopes of different elements: uranium-238, radon-222, lead-210, and then you can see on the right-hand column, we have the amount of half-life, the amount of time it takes for that isotope to become 50% stable. So you'll notice that there's a huge variation in time. We have uranium-238, which takes 4.51 times 10 to the power of 9 years. Okay, let's take a look at that number for a second. We haven't reviewed scientific notation in class just yet, so let's write that number out so you can see just how large it is. So 2, 3, 4, 5, 6, 7, 8, 9. That is 4,510,000,000 years. That's how long it takes uranium-238 to decay to a more stable isotope by 50%. Whereas if we take a look at another isotope, let's take a look at polonium here, polonium-214. Notice its half-life is a fraction of a second. So if you break this down into normal notation, take it out of scientific notation, this is equal to 0.00016 seconds. Okay, so that is a very, very short half-life. The shorter the half-life for an isotope, the more unstable the isotope is. Also, half-lives are unaffected by external conditions such as temperature, pressure, or state of chemical combination. So right now in this unit, we're talking about nuclear decay, nuclear reactions. So nuclear reactions involve subatomic particles located inside the nucleus, which are the neutrons and protons. When we talk about chemical combination, we're talking about electrons. Electrons are involved in chemical reactions and chemical bonding, and they are unaffected by nuclear decay. Let's take a look at another graph. So this graph shows you the fraction on the y-axis of the original element instead of a percent. So remember, this can be this amount here. Sometimes if you may see a percentage. So understand that 1 out of 1 just represents the whole sample. This is the whole sample. Or you could say it represents 100% of the original mass, of the initial mass of the sample. And sometimes you may just see it expressed as 1, because 1 divided by 1 is just 1, right? So if you don't see a mass in this spot on the y-axis, you may see fraction or ratio or percentage. Okay, so just be aware of that. So we're looking at the radioactive isotope carbon-14. And you'll notice in the first circle, okay, 100% of the atoms represented in that circle are carbon-14 atoms. If you count up all the little light gray, or we'll call them white dots, okay, if you count them all up, we have a total of 8 carbon-14 atoms. Okay, so carbon-14 has a half-life of 5,730 years. So if you look at the x-axis, we're starting off at time 0. So at the very beginning, when we are looking at our initial sample, before any time has passed, at time 0, we have 100% or the whole sample present. After the first half-life, which is 5,730 years, we have half as many carbon-14 atoms present. So go ahead and count up the lighter circles, the white circles. So we have 1, 2, 3, 4. So we have 4 carbon-14 atoms. I'll just circle them for you so you can see which ones I'm counting. So we have 4 carbon-14 atoms. And notice the time at the bottom, it's expressed in half-lives. So if the carbon-14 atom has a half-life of 5,730 years, that means after one half-life, 5,730 years have passed. That much time has elapsed. Now let's look at two half-lives. So two half-lives mean that another 5,730 years have passed. So we're simply going to add this number, this amount of time, to figure out how much time is in two half-lives total. So after 11,460 years, so two half-lives, we now have half of the sample remaining. So 4 divided by 2 is now 2. So if you count up the white circles again, I'm just going to circle them here so you can see which ones I'm counting. We have 2 left, okay? So you can see that on the y-axis, the fraction is showing up as half for the picture that shows 4 nuclei of carbon-14 left. And then we have 1/4 the amount that we had to start with after the second half-life. And then we're going to look at one more decay process. So after another 5,730 years, okay, you're adding that number to the 11,460. That's 3 half-lives that have passed, and that's a total of 17,190 years. So half of the 2 is now 1. So we have 1 radioactive nuclide of carbon-14 remaining. The rest of it has changed into the stable nitrogen-14 atom. Now, let's take a look again at the fraction really quickly. So notice the 1 out of 1 up here on the y-axis. So if we're looking at each of these as a fraction, the 100%, the whole sample can be represented by 8 over 8. 8 over 8 equals 1, right? That's 100%. Then after the first half-life passes, we have half, or 50%, of the initial amount. So 4 out of 8 equals half, right? And then in the third picture, we have 2 out of 8. So 2 out of 8 simplified is 1/4. And then finally, the last picture shows 1 particle out of 8 is still carbon-14. So that is represented in this fraction here. And the decay process will continue so that the carbon-14 amount divides in half every time. And it'll continue to approach 0. Here's another graph that we can take a look at. So in this graph on the y-axis, you're shown a ratio of remaining potassium-40 atoms. So the potassium-40, 100% of it, or 1 out of 1, the total potassium is shown here in this picture as red dots. After 1 half-life, which take a look at the amount of time in 1 half-life for potassium-40. It's 1.3 billion years. That's a really long half-life. That's a very stable isotope. It's still radioactive. It's still undergoing nuclear decay, but because of that long half-life, it's considered a more stable isotope. So you'll notice that after the first half-life, after the 1.3 billion years, we have about half as many red dots in the second picture, okay? The potassium-40 is decaying to form a more stable isotope of calcium-40, okay? And then what's happening is after another half-life passes, so you add 1.3 billion to get the 2.6 billion years in another half-life. Okay, so after 2 half-lives, we have 1/4 the original amount. Okay, so once again, this is half right here, half the original amount, and this is half times half, or 1/4. Okay, so that's 2 half-lives. After 3 half-lives, which is not pictured here, you would have half times half times half. That's 3 half-lives, or 1/8. And then finally, after 4 half-lives, you'll notice that most of the potassium-40, after 5.2 billion years, right, add another 1.3 here, and we get 5.2 billion years. After the 4th half-life, there's only 1/16 of the original sample present. So that's half to the power of 4. We can use exponents when we get to the point where there's too many halves to write. So half to the power of 4 is 1/16. For those of you that are very observant and notice that there are more than just potassium and calcium atoms represented in these circles, I will share with you that potassium 40 actually undergoes two types of decay. So 89.1% of the sample of potassium 40 is undergoing beta decay. Okay, so where an electron or beta particle is emitted and the number of neutrons is reduced, making the proton number increase. The other 10.9% undergoes another process of nuclear decay called electron capture, where some of the potassium 40 becomes argon 40. Okay, so they're both nuclear decay processes, and both of these reactions are happening simultaneously. That's not something that you need to know for this course. What's important about this diagram is just focusing on the exponential decay of the graph, how it's decreasing. The slope is decreasing as you move along the number of half-lives, as you move along the x-axis, and it's the amount of the radioactive sample decreases by half with every passing half-life. Now let's take a look at another way of presenting data. So given the isotope strontium-90, remember 90 in this isotope name just represents the mass number. It's not the actual given mass of the sample. This is simply the mass number of the isotope. And when an isotope name is written, it's always part of the name. The half-life of strontium-90 is about 29 years. So if we're looking at the amount of time, the amount of the radioactive isotope left over after 4 half-lives given a sample of 10 grams, we would start our table with the elapsed time of 0 and the number of half-lives being 0. Okay, so 10 grams here represents our original amount. This is our original sample. 10 grams represents 100% of the original sample. Okay, after 1 half-life has passed, okay, how much time has elapsed? 1 half-life. Hopefully you can tell that it's 29 years because 29 years is the amount of time 1 half-life. So after 29 years, we will have half of the original sample. So what's half of 10 grams? 10 grams divided by 2. 5 grams. Okay, so you can express this when you're showing your work. You can express it as 10.0 times 0.5. You can express this as 10 divided by 2 or 10 times 1/2. So you can show your work in multiple ways. After the second half-life, okay, all we're doing is we're adding another 29 years, okay, to figure out the total amount of time that has passed. That's 58 years. So after 58 years, how much of the original sample is left? Well, there's a couple ways you could do this. You could take the 5 grams and divide it by 2. Or you could just simply take the original sample and multiply it by half 2 times. Another way you could do this is say 10 grams times half squared. Or if you're putting this in your calculator, you can just do 0.5 squared times 10. Okay, so that will give you 2.50 grams, however you decide you want to do that. After the third half-life, okay, we're going to add another 29 years to 58 to figure out how much time has passed after 3 half-lives. So 58 plus 29 is 87 years. So after 87 years have passed, how much of the original sample remains? So again, you could divide 2.50 grams by 2. Okay, or you could show your work this way. Notice we have half times half times half. So that is the same thing as saying half cubed. Okay, and we get the number of halves from the number of half-lives. So 2.5 divided by 2 is 1.25, or you could just simply take the original sample and multiply it by 0.5 cubed, and you would get this amount. Okay, one more. After the fourth half-life, all we're doing is adding 29 more years to 87, and that will give us 116 years. So after 116 years have passed, how much of the original sample do we have? So you could simply take 1.25 and divide that by 2. Okay? Or you could do, because there's 4 half-lives, you could do half times half times half times half times the original mass to get 0.625. Okay, and then if you wanted to use an exponent, you could also say that this piece can also be expressed as 0.5 or half to the power of 4. So this is an example of how you can determine the amount of radioactive sample that remains after a certain number of half-lives have passed using a table to organize your work. Another question that could be asked is if after 4 half-lives we have 0.625 grams that is still radioactive, so this is still unstable. This is the strontium 90 that remains. Okay, so this is the remaining radioactive isotope. Another question that could be asked is how much of the original sample, how much of the 10 grams has stabilized? So think about how you would figure that out. After 4 half-lives, how much of the original sample has stabilized? So the way you would figure that out is you could take 10 grams, the original sample, and subtract 0.625 from that number, and that would give you the amount of sample that has stabilized. So take a moment, use your calculator to figure out how much has stabilized. Hopefully you found that the answer is 9.375 or 9.4 grams is stable. Sometimes it's helpful to use an algebraic expression to solve for the different variables in half-life problems. So this is an example of an optional equation that you can use if you find it helpful. Otherwise, you can simply stick with the table or chart to organize your work. So the m sub f represents the final mass of the isotope, the m sub I represents the initial mass, and the n here represents the number of half-lives. So if you are comfortable with algebra, it will be very simple to solve for the final mass and also very simple to solve for the initial mass. The calculating n requires additional steps on your calculator, and if you have not covered that, how to solve for exponents yet in your algebra classes, then you may want to opt for the chart to show your work. In this example, we're going to attempt to use the equation. So in this problem, we're given a half-life. Fluorine has a half-life of 5 seconds, and we're going to write our given values in this table. The initial mass, we're starting with 25 grams, so that's going to be our initial mass. How many grams? So our final mass is our unknown, because how many grams would remain? That's how we know that's our final mass after 60 seconds. So 60 seconds represents our total time. So the first step is to write our equation. So that's the equation we're going to use, and we're going to plug in our numbers. Now we have the initial mass, and we know that we're solving for the final mass, but what we're still missing is this value here, the n. So how do we solve for n? N, remember, represents the number of half-lives. So we are given all the information we need to figure out what n is. You have the total amount of time, 60 seconds, and you have the amount of time in 1 half-life. So the way to solve for the number of half-lives is simply dividing those values. So 60 seconds representing the total time divided by the amount of time in 1 half-life will give you the number of half-lives. So this is a step that you will often need to calculate before you can attempt any of these half-life problems. Okay, so let's go ahead and plug in our numbers. 60 divided by 5 gave us 12, so that's how we know what the value of n is. We have 12 half-lives that passed, and remember half is just 0.5, so when you're entering this work into your calculator, you can go ahead and solve and record your final answer. So hopefully you got 0.00610 grams as your final answer. Don't forget to label your answers. So the question's asking for grams, so that's how we know to put grams as our answer's final label. And notice the number of digits, 25.0 grams is the value given to us. So that's 3 significant digits given to us in the value for mass. And since we're solving for mass, we will also stick with the 3 significant digits there. Okay, if you wanted to express this in scientific notation, you could simply write 6.10 times 10 to the negative 1, 2, 3, negative 3 grams. So that's another way you could express your answer. Let's look at another example. Carbon 14 has a half-life of 5,730 grams. So that's one of our given values. How much of a 100-gram sample, so that is our starting mass, our initial mass, will remain. So we don't know the final mass, that's what we're solving for, after 17,190 years. So our total time that has elapsed is 17,190. So we're going to follow the same step to calculate the number of half-lives. So the total time, again, is the larger amount of years divided by the amount of time in 1 half-life, 5,730. That's going to give us 3 half-lives. This time, we're going to try to use the table to solve instead of the algebra. But again, you can use whatever way is more comfortable for you. So we'll start with setting up 2 horizontal rows. If you prefer columns, vertical columns, you can you can arrange your data into columns. So remember to label your mass as grams, if that's the given value. And then we'll say half-lives will be the second, the title of the second row. So at half-life 0, we always start at 0 half-lives. Just like on the graph, we always started at 0 half-lives. Same thing here. So at 0 half-lives, we have our original mass, 100 grams. So we're going to show that in our table. Then after the first half-life passes, right, we will have 50% or half of the original mass amount. So half of 100 is 50 grams, okay? And then we're going to go on to the second half-life. So after the second half-life, we will have half as much as we have here. So 50 divided by 2 is 25. Now, how do I know when to stop? When do I stop dividing in half? Well, that's where this number comes in, the 3 half-lives. This is how I know when to stop. So right now, we've experienced 2 half-lives. We're going to move on to the third, and that's our stopping point as calculated in our given value section here. So after the third half-life, we have half as much left. So 25 divided by 2 is 12.50. So that represents the amount of the original isotope that remains after 3 half-lives, or after 17,190 years. Let's take a look at practice 4. A patient is administered 20 milligrams of iodine 131. So this is going to be our initial mass. This is what we're starting with. So initial mass. After 24 days, so this is the total time that has passed. So total time, 2.50 milligrams of the sample remains. So this is our final mass, so M sub F. What is the half-life? So we don't know T 1/2. What is the half-life of iodine? Since we are not given 2 time values, we're going to go ahead and begin this problem using our table. So mass is going to be my top horizontal row. Mass is given to us in milligrams. And our bottom row will be the number of half-lives. So half-lives, okay? Now, we always start at 0 half-lives, okay? Don't forget that. This is a common mistake. People forget the 0. So at 0, that represents the beginning. No time has elapsed. At time 0, we have the original amount or the initial amount, which is 20 milligrams. So we'll start there. 20 milligrams is present. After the first half-life, okay, we have 10 grams that remain. 20 divided by 2 is 10. That's half of 20. Okay, after the second half-life, we have half of 10, which is 5.00. Now, how do I know when to stop? When do I stop dividing by 2? Well, take a look at the final mass given to you, 2.50. That's when you stop, when you hit that number. So we're going to keep going. So after the third half-life, 5.00 divided by 2 is 2.50. So that's our stopping point. So this value tells us that 3 half-lives have passed in order to reach the 2.50 milligram sample that remains. So it took 24 days for iodine 131 to decay to 2.50 milligrams. That was 3 half-lives. So 24 days spans 3 half-lives. And the question's saying, what is the half-life? So how much time, how many days are in 1 half-life of iodine 131? So you would divide these two numbers, 24 days divided by 3. That gives us 8 days per half-life. So that's our answer. Our next problem shows titanium 51. It has a half-life of 5.76 minutes. So this is T1 half. How much total time, so the total time is what we're solving for, would it take for 50 gram sample, for a 50 gram sample? So that's going to be our initial mass, titanium 51 to decay to 6.25 grams. So this will be our final mass. Okay. So once again, we don't have both values for time. So because of that, we're going to go right into our chart. So the mass is given to us in units of grams and half-lives at the bottom here. Always start at 0. Make sure you do that. At 0 half-lives, we're starting with the original amount, the initial mass, which is 50 grams. Okay. After the first half-life, okay, we have 25 grams that remain. After the second half-life, we have 12.5 grams that remain. So when do I stop? Dividing by 2. Take a look at your final mass. Your final mass is 6.25. That's when you stop. Okay, after the third half-life, 12.5 divided by 2, that gives us 6.25. So this is where our stopping point is. Now this is showing us that after 3 half-lives, we end up with 6.25 grams. The question though is saying how much total time would it take? So it took us 3 half-lives to get to the stopping point. And if we know that there are 5.76 minutes in 1 half-life, that's given to us in the problem, okay, all we have to do is multiply 3 times 5.76. So we can cancel out the half-lives, multiply across, and record our answer. Pause the video to see if you can calculate this on your own. 3 times 5.76 is 17.28. We're going to go ahead and round that to 17.3. The half-lives cancel, and we end up with minutes. So 17.3 minutes is the total time. Let's look at our next problem. Iron 59 has a half-life of 44.5 days. So this number here represents the T1 half. What fraction? So this time we're not looking for an actual final mass or an initial mass for that matter. We're just simply looking for a fraction or factor of iron 59 that will remain after 133.5 days. So this number here represents our total time. So we'll start this problem by dividing the total time divided by the amount of time 1 half-life. So that's 133.5 days. It's always going to be the larger amount of time over the smaller amount of time. 44.5 days. And this will be true for the problems that we are going to be solving in this class. So 44.5 days per half-life. Okay. When you divide these numbers, you should get 3. The days cancel. Okay. 3 half-lives. 3 half-lives will have passed. But the question's saying what fraction will remain. So you know that 3 half-lives means we will need to multiply our sample by half 3 times, or you could say divide by 2 3 times. This is the same thing as saying half cubed. Okay, so go ahead and do that on your calculator. Half cubed equals 1/8. So 1/8 of the sample will remain. And when we say will remain, we mean it will remain radioactive. This problem is similar to the one on the previous slide. The half-life of copper-66 is 5.10 minutes. So this is our half-life, T1/2. What fraction or factor of the initial mass would remain after 51 minutes? So 51 minutes represents our total amount of time. So once again, we're going to take our total time and divide that by the amount of time in 1 half-life. That would be 51 minutes divided by 5.10 minutes in a half-life, per half-life. So if you divide those on your calculator, hopefully you will see that 10 half-lives is the amount of time that will pass, or 51 minutes is 10 half-lives. Now, the question's saying what fraction will remain, or what factor will remain. So understand that given an initial sample, you would need to divide that quantity in half 10 times because of this value. But we're not given an initial mass. We're not given a number of grams or milligrams. So we will just have to take the half and multiply this 10 times. Or you could simply use your exponent key on your calculator and do it that way. So half to the power of 10. Also, you could just do 2 to the power of 10 on your calculator. And once you solve, you should get 1,024. So 1 over 1,024th of the original sample will remain radioactive. The rest of it will be stable. The half-life of thorium-227 is 18.72 days, so we have the half-life given to us here. How many days are required for 75% of a given amount to decay? In this problem, we are not given a mass or an actual number of grams. Instead, we're given percentages. So let's just review to make sure we understand what these percentages actually mean. 100% will represent the initial mass or the total isotope sample. So 100% of it before any time has passed is radioactive. After a certain amount of days, that's what we need to determine. We don't know the total amount of days that have elapsed. Only 75% of the isotope will have decayed. So 75%, when we say it's decayed, that means it's become stable. So 100% minus 75 equals 25%. So 25% will remain radioactive or unstable. So our objective in this problem is to figure out how many days have passed. So if 25% remains radioactive, that means 1/4 of the sample is still radioactive. To get 1/4 of the sample to remain radioactive, that means 2 half-lives need to have passed. Half times half equals 1/4. So this is 2 half-lives. So if we know 2 half-lives have passed, and the half-life of thorium is 18.72 days, all we need to do is multiply 2 half-lives by 18.72 days, because that's how many days are in 1 half-life. And I know to multiply because when I set my units up this way, these units cancel. So 2 times 18.72 days. Take a moment and pause the video to do that on your calculator. Let's take a look at practice number 9. If plutonium-239 has a half-life of 24,000 years, that's our T1 half, how much of a 10.8 gram sample, that's our initial mass or starting mass, would remain after 2 half-lives? So we're looking for the final mass. We don't know the final mass, but we're given 2 half-lives. So you can use algebra to solve if you like, but not completely necessary. And the reason why you can use algebra is because we're given that n equals 2. Remember, n is the number of half-lives. So now let's take a moment and set up our table. Mass is going to be in our first row, and that's given to us in grams. So make sure you label that. And then the bottom row, we'll call that half-lives. We already know our stopping point will be 2 because it gives us that in the problem. So don't forget to start at 0. At 0 half-lives, we have the original mass, which is 10.8 grams. And then after the first half-life, we have half that amount, which is 5.4 grams. And then after the second half-life, which is our stopping point, we have 2.7 grams. So we've reached our final mass of 2.7 grams. That's how much that would remain after 2 half-lives. In this problem, we're going to focus on the graph, analyzing the data. So we're going to use the graph to determine the half-life of this isotope, magnesium-28. So take a look at the X and Y axis. On the X axis, we've got time represented in hours and fraction remaining on the Y axis. So if you zoom in, and if you remember that the 1 represents the entire fraction, so 1/1, that's 100% of the sample that we're starting out with. As 1 half-life passes, we'll have 0.5 grams of the sample remaining. So you should go down to the 0.5, and then if you go over to the curve, you'll notice that we're just a little bit ahead of the 20-hour mark. So if you want to call that 21 hours, that would be an acceptable amount of hours to record as the number of hours in 1 half-life. Also notice that if you look at the second half-life that passes, so 21 more hours, we end up at the 42. So after the second life passes, we'll have 0.25 or 1/4 the original sample. So if you look at where that point is on the curve, you'll notice it's at 42. So that's another way for us to confirm that 21 hours is in fact the half-life for magnesium-28. So you can see the increments between The first half-life and the second half-life are the same. Also, when I copied and pasted this graph over, it gave me the chart, the data that comes along with it. So you can see in the chart, and it's 21 hours when we have half the sample remaining. Now let's take a look at how much magnesium-28 remains undecayed after 35 hours. So 35 hours, find that on the x-axis. You can see it marked there. And follow it up to the curve, and you'll see that that's 0.3 on the y-axis. 0.3 is the fraction that remains radioactive. So that would be our answer to that second question. So remember, undecayed means that that amount is still radioactive. It's still unstable. Now the next question asks us about magnesium-28, how much of it has decayed after 70 hours. So let's take a look at the graph after 70 hours has passed. And this is how much has decayed. So if it's decayed, that means it's now stabilized. So this fraction of the isotope is stable. So let's take a look at 70 hours on the graph, okay, and see where it matches up to the curve. The y-axis reading is 0.1. So 0.1 is the fraction of the isotope that still remains radioactive. Now remember, the entire sample is represented by 1. Okay, so if 0.1 is the unstable remaining isotope, okay, so you would subtract the total, 1 minus 0.1, to figure out the amount that has actually decayed or has actually stabilized. So 1 minus 0.1 comes out to 0.9. So 0.9 is the fraction of the isotope that has stabilized. So you could say 0.9. You could also say that that is 9/10 that is stabilized, or 90%. So just understand how the fraction or the decimal can also translate into a percentage. Lastly, we're going to take a look at reviewing how to write nuclear equations in writing the nuclear equation for the beta emission of magnesium-28. So remember how to write the symbol for this isotope. Mg is the symbol for magnesium. 28 is given to us as its mass number, so we'll write that at the top. And at the bottom, remember, is the atomic number. So look it up on the periodic table and write down the atomic number for magnesium. It's 12. So the statement above says it's a beta emitter. So we're going to draw an arrow and then show a beta particle being released. So remember, the beta particle has no mass and it has a charge of -1. The symbol to represent a beta particle is E, that of an electron. Then we're going to add to that the daughter isotope. So remember, the mass does not change when a beta particle is released, so it's still going to be 28. But notice the atomic number is going to change. So what minus 1 is going to give us 12? 13. Yes, 13 minus 1 will give us 12. So use that number, 13, to look up the element on the periodic table. 13 would be the atomic number of the element of the daughter isotope. 13 belongs to aluminum. So now let's take a step back and see how all of these numbers are connected to this equation. When we say that a daughter isotope, a stable daughter isotope of aluminum-28 has formed, we're talking about the 0.9. The 0.9 is the fraction that has decayed of magnesium-28, forming that stable daughter isotope. So then 0.1 would still be radioactive magnesium-28. And that's it for half-life.